In this lecture, we are going to talk about another application that we want to optimize, which is video and also generative models. Right? So this is the big picture of the third section of our lecture, from inference to training optimizations all the way to application-specific optimizations. Okay? And let's see where we are. So in last lecture, we talked about the point cloud acceleration. Right? So point cloud widely used autonomous driving, spatial sparsity, and spatial redundancy. We talk about several techniques to accelerate point cloud applications. Today, we are going to talk about how to accelerate video understanding. Right? So adding the spatial dimension, that's the point cloud. Adding the temporal dimension, that's the videos. And JSON frames has a lot of redundancy, a lot of similarity, and we want to take advantage of those temporal redundancy to accelerate video understanding. In the second half, we're also going to talk about how to accelerate those generative models, those GANs. And in the next lecture, we're going to talk about how to accelerate natural language processing and transformers. So let's start with section 1, which is accelerating video understanding. And this is the agenda for accelerating video understanding. First of all, using what we have learned so far, using 2D scenes for video understanding. And then we talk about how to use 3D scenes for better video understanding. Followed by introducing our work, which is temporal shift module, which use 2D cost but offer the 3D convolutions accuracy and performance. Finally, we'll introduce other efficient methods for video understanding. Okay, some background. So video is growing very exponentially recent years. There are tons of hours of videos uploaded to YouTube every day, right? So efficient video processing is very essential for both the cloud and also the edge devices. In several scenarios, like in hospitals, the privacy matters a lot, so we have to process those videos locally on the edge device, on those IoT devices, or on the phones. But those devices, again, has limited computation capability and also may suffer from energy and speed latency constraint, right? So we want to bridge the gap between the demand for computation versus what the edge device can offer. And video understanding has a lot of applications. So for example, action and gesture recognition, right, over there. And also scene understanding and video search for ads. You want to search the video on YouTube, for example. And also video prediction for autonomous driving. You want to predict the motion, the intention for the pedestrian, for the car, from the past video frame to predict what is going to happen in the future video frame. So these are some of the applications for video understanding. And those tasks can be roughly categorized into online and offline categories, right? For example, like action and gesture recognition, some of the cars are already equipped with those virtual hand gesture-based recognition to tune the knobs of the car. So those has to be online recognition, right? On the contrary, those video understanding for search for ads, those could be performed offline, right? You can spend overnight to process this video, and the other day we can do video search, right? So we are going to cover both the online and the offline video understanding. So let's brainstorm a little bit. What's the difference between the video understanding versus the image understanding, which we have learned so far? Let's see from this example. Actually, this is putting something from left to right, right? We have a tape, it's a piece of paper. We are putting the tape from left to right. By looking at a single frame, just looking at a single frame, we actually don't know whether we are putting something from left to right or from right to left, right? So that's the difference between video understanding versus image. We cannot just look at a single image and then determine what is happening in this video, right? So temporal modeling Okay, understand the temporal information, not only the spatial information, is the key important stuff for video understanding. Therefore, let's brainstorm a little bit. How can we use what we have learned so far, like 2D scenes, to understand the videos, to take into account this temporal information? Yeah, we can just make the convolution 3D, right? Not only shift around the spatial dimension, but also we can move the convolution kernels along the temporal dimension. That may add some computation, but of course you can do the temporal modeling.
You can expand your input space with the previous 2 frames, or however many you like.
Right, you can put your frame in the context. For example, you can concatenate previous frame and future frames, and do the convolution across the channel dimension. Put them in the so that you have the context. Right. Right. Those are all very good ideas. Basically, you want to not only consider a single frame but adjacent frames. Right. So the simplest solution is actually just using pure 2D convolutions for each frame. Okay? Each frame individually, do the prediction, and finally aggregate the score in the very end. Right? We can imagine this is as the same as batch processing a group of input images. Right? So it is pretty efficient. We just do very late fusion, late aggregation, right? Either do the average or the max to find the aggregated score of each individual frame. Very simple. Then there's another method that combines 2 streams. Okay, so the first is the spatial, just the raw images. Okay, and then the second stream is actually the optical flow. Right. So what is the optical flow? At each pixel, we have a two-dimensional tensor indicating the difference between the pixel from the previous frame and the next frame. Right. For example, if this person is moving something, it's going to show the direction of each pixel. Right. So that captures some low-level information between the movement from the previous frame and the next frame, right? So therefore, we can have 2 streams. One is the spatial stream. The other is the temporal stream. And finally, we aggregate the result in the very end to give the fused class score. So this is another way to consider this temporal information by introducing this optical flow. There's another method, right? So previously we were just doing the raw average of the prediction of each frame. So remember, we have this long short-term memory and or RNNs. Okay, so here we can also use LSTM to do the temporal modeling. So at each timestamp, we have the CN features. Okay, and finally we can feed it to the LSTM to model the temporal information. Okay, so those are several 2D-based methods. We can summarize the pros and cons.
Use another CNN instead of an LSTM in that last post-fusion part, so 1D CNN. Or would that not work?
Oh, that's another idea, right? Actually, we'll talk about those ideas that use separate kernels for temporal and spatial modeling. That's a good idea. We'll talk about that idea very soon by decomposing the 3D scene into a 2D scene for spatial modeling and a 1D scene for temporal modeling. Yeah, that's a very good point. So the pro of using those 2D scene-based method is that they are very computationally efficient, right? Just batch processing a bunch of images, okay? And we can reuse those 2D scene kernels for video recognition. And what is the con here? So if using the first method, which is just passing each frame individually and do the averaging in the very end, the accuracy is relatively low, cannot model those temporal information from the beginning. The fusion is just too late. For the second method that requires optical flow, actually calculating the optical flow itself is pretty computationally intensive, so it's not computationally efficient. Or we can do using a LLCM, but such late fusion cannot model those low-level temporal relationships either. So therefore, we are going to shift from 2D scenes to 3D scenes for video understanding. So what is a 3D scene? So in 2D convolution, we move the convolution kernel in 2 dimensions, the x dimension and the y dimension. So in this work called C3D, okay, so we convolve not only the spatial dimension, but also the temporal dimension, right? So we are moving not only in the h and w dimension, but also in the temporal dimension. Okay. So what is the dimension of the convolution kernel in this case? So for 2D scene, but we discussed like AlexNet, VGG, what is the dimension of the convolution kernels? It's 4 dimension, right? We have 3 by 3 by input channel by output channel, right? So what about in this case, in 3D convolution, what is the dimension of those 3D convolution kernels? Yes, 5. Since we have another dimension for the temporal dimension, we have to shift, right? And as you can imagine, you add another dimension that's very computationally intensive and also add a lot of storage to store those kernels, right? So on top of that, this I3D, okay, introduce another approach that can initialize those 3D scenes using the 2D scenes weight, right? So the motivation is that ImageNet provides a very good pre-trained model, very good pre-trained models for 2D scene. But now we want to apply that to 3D. How can we utilize the pre-trained ImageNet model, which is 2D, for these 3D models? Okay? So we just uniformly initialize each timestamp. For example, we have 3 by 3 by 3, like 3 frames in the temporal dimension. We just initialize all those t dimension kernels using the pre-trained ImageNet model. Okay, so initialize 3D scenes with 2D scene weights. Okay, like those are trained on ImageNet, which we call it inflation. Like inflate from a 2D kernel into a 3D kernel by repeating among the temporal dimension. Okay, and we repeat the weights across the temporal dimension for initialization. Okay, so although we still have this 3D kernel, but we can initialize that with 2D kernel so that we can train it faster and also take advantage of the pre-trained ImageNet models. And as you can see, previously we have 7 by 7 kernel. Now we have 7 by 7 by 7 kernel. 3 by 3 kernel. Now we have 3 by 3 by 3 kernel. So what is the pros and cons for such 3D-based scene for video understanding? So of course, we have better accuracy by being able to jointly model the spatial and also the temporal information by introducing 3D convolution, right? We can model those low-level, mid-level, and also the high-level information since we are using 3D convolution from the beginning by fusing different temporal frames rather than fusing them very late. However, like we discussed, the cost is pretty high. Right? We introduced another dimension. We have 5-dimensional kernels, right? Model size and computation both increased due to the extra temporal dimension.
Say low, mid-level, and high-level information. What exactly is an example, or what does that mean?
Yeah, like let me give you an example. For example, the edges and corners, those are low-level features, right? Some like a wheel, like something round, something some circle. Those are slightly high-level, mid-level information. And what are high-level informations? For example, both bicycle and car can move, moving objects. Those are some high-level concepts. Okay, those are something that is in the spatial dimension. Okay, in the temporal dimension, you can imagine something is moving left, something is moving right. Those are like low-level information. But you can imagine something that's moving moving from Boston to New York. Those kind of more high level, you have to associate that with some high level concepts. Those are high level information. Yeah, but those are all relative, right? And so can we achieve 3D scenes performance at a 2D scenes cost, right? So that is the goal for reducing the computational cost for video understanding. So we'll introduce this cool method called temporal shift module, which is a very effective method that have the best of both worlds by having 2D scenes cost and a 3D scenes performance. So temporal shift module is actually a zero flop, okay, and zero parameter for temporal modeling. So conventionally, say we have a T1, T2, T3, and T4. Okay, we have 4 timestamps, and this is in the channel dimension. This is the T dimension, okay, and this is in the H and W dimension, which we annotate them using combine them into only one dimension. Okay, so originally we have a temporal channel H and W. Those are 4-dimensional tensors. Now we are using only 3-dimensional tensors to represent them by fusing H and W into a single dimension, right? So in this annotation, we actually want to mingle the information from the previous frame and the next frame. So current frame can have the information for both the past and also the future. Okay, so let's see what it does. So we can actually shift among this temporal dimension. Okay, so originally this T1, T2, T3, T4, but now we shifted to the shifted down, okay, by one step, and here we are shifting it up by one step, right? So let's see what happens to T2. Now T2 has information for both. This is T1. This is coming from T3, right? So T2 now has both T1 and T3's information. Okay, so we can run convolution using on top of this tensor, okay, which effectively combined partial information from the previous frame and the next frame. Okay, so why we are only moving here 1 out of 6 channels? Can we move more channels? What is the pros and cons here? We shift a small amount of channels versus can we just shift all the channels? Yeah, exactly. We also want the current frame's spatial information, right? So this is a trade-off between spatial modeling and temporal modeling, right? So here we are having the previous frame, the next frame, but we still need a lot of information for the current frame, right? So empirically, we are using 1/8 about the channels to be shifted. That is going to be shifted, right? So what is the computation overhead here? Actually, we didn't introduce any weight parameter, unlike 3D convolution. You expand the kernel by adding another dimension. But here, there's no hyperparameter, there's no weight, right? And does it have any flops? Actually, we don't have to do any computation, right? We just shift. We don't have to do any multiplication or add just to perform this shift. And later we can do the 2D convolution on each timestamp the same as before. Right? So what is the limitation here by such offline temporal shift? So we are both shifting the past to the current frame and also shifting from future frame to current frame. This is okay for offline video understanding since we have all the frames, right? But what about online video understanding? We only have the past frame, so we can shift from past frame to the future, to the current. But we don't have access to the future frame since this is online video understanding. At the current frame, we don't know what's going to happen in the future. So luckily, we can use the single directional, unidirectional temporal shift, rather than this bidirectional temporal shift. This is for offline video understanding. This is for online video understanding. Okay, so you need bidirectional temporal shift, unidirectional temporal shift. Okay, from past to current, from future to current. This is from past to current only. Okay, so far so good. All right. So let's see the application to offline TSM module first. So we have multiple frames. This is the T dimension, okay, and then we are going to use 2D convolution for each temporal frame. Okay, so now we can process them in batch size of 4, okay, 2D images, and then we are going to do the temporal shift to shift the tensor a little bit. We also tried this rotational shift, but actually that doesn't help. We can just throw this part away, okay, and pad with the zeros. And we have a bypass layer, which is very crucial to compensate for the information loss for these four channels, okay, using this bypass. So that is one TSM module that can be injected into any different backbone. We can use Resin 50. We can also use MobileNet, no matter which architecture we use, that is orthogonal, what kind of convolution we are using versus this shift operation. Okay, so this shift operation can be inserted into any different backbones. And this is the online version. Okay, in the online version TSM, we have when we are at FT, we don't have access to FT plus 1. Okay, so this is the layer dimension. Okay, we have multiple convolution layers. So rather than using purely the current timestamps feature, we are combining previous timestamps feature that is combined with the current timestamp, okay, by fusing them in the channel dimension. So we have information not only from current frame, but also the past frame. Okay? Not only current frame, but also past frame. But the past frame also has the information of the past frame. Right? So altogether, you have access to the entire history for temporal modeling. And the implementation is very straightforward. Just a couple of lines of Python code. Now you can turn your 2D scene into a like something you can understand the videos. Okay, so from the first fold, we shift left. Second fold, we shift right. And the remaining channels, we do not shift them. Okay, just very simple tensor operations. So there is one hyperparameter. You have to decide the folding divisor, right? Are you shifting 1/4? Are you shifting 1/8? So that's a hyperparameter we discussed to trade off between how much information you want to keep for the current frame versus how much information you want to get from the past frames and the future frames. Okay. And actually, this method is quite computationally efficient. So compared with the i3D plus these non-local methods that require 600 gigaflops per video, TSM can require only 100 gigaflops per video. Okay, almost 1/8 of the computation, okay, but with even higher accuracy. And the size of the circle indicates the model size. Okay? TSM apparently has both smaller computation and also a smaller model size. So this is showing the speed. Okay, so the i3D method, like we mentioned, using the inflation method that inflate a 2D scenes pre-trained ImageNet, inflate among the temporal dimension, and then we can do 3D convolution. So each video requires 164 milliseconds to process. Okay, and the accuracy is about 41.6%. But using TSM, it's much faster. Okay, 17.4 milliseconds per video, and the accuracy is even higher. So this is comparing the throughput. So each row is a bunch of videos, and we have a lot of rows. Okay, the white ribbon is showing we are currently processing this row of videos. Okay, so using the baseline i3D method, it can process about 6 videos per second. Okay, pretty slow. But using TSM, we can actually process 77 videos per second. So it's almost more than 10 times faster, higher throughput. Okay, so for example, in one night, if you can process 1 million of videos, now we can process 10 millions of videos using the exact same hardware resource. Okay? So those are the offline video understanding. What about the online case? So if something happens, say we have some camera, we want to detect whether some malicious people is trying to enter our yard. So we want to recognize those malicious actions early, right? Someone is fighting, something get broken, for example. So we want to, given 100% of the video, we want to observe something. Even when we are watching like 20% of the video, we hope we are able to find what's happening in the video by watching only partial video. Okay, so these are the baseline methods. The accuracy degrade very quickly as we are watching like 20% or 10% of the video. But the accuracy for TSM maintains pretty well, even though we are watching only 10% of the video. We can still determine what is happening at about 90% accuracy. So this is for early video recognition. So by combining those temporal information, it also helps with other tasks such as detection, right? So for this car, the baseline model sometimes mispredict the car as a train, maybe because of the high beam light, which usually happens in the train. But TSM is pretty robust, even with high beam light, since it has the temporal information, knowing that the past frame it is a car, for the current frame it can also only become a train, right? So this is without temporal modeling. Okay, this is with temporal modeling. This is frame by frame prediction. This is combining different frames linked by the temporal shift. And this is some analytical model showing the latency comparison. We are maintaining the latency while achieving even better accuracy than those past methods that incorporate temporal modeling. Temporal shift module is pretty energy efficient. Actually, we can use the LED bulb level of power, just a few watts, 4 watts, 5 watts on just a nano. We can actually, on the GPU, can perform 74 frames per second. Even on the Raspberry Pi, at that time, we can perform 14 frames per second. And recently, after our kernel optimization, we can accelerate this actually at 30 frames per second on the Raspberry Pi using the mobile V2 backbone, okay? Which can enable a lot of gadgets to understand the video. Okay? So if you want to try such a video understanding in your final project, feel free to contact us. We can give you either some Raspberry Pis or some phones if you want to do some activity recognition. Okay, so we want to be coherent for our lecture, not only cover inference, but also training, right? So training those large-scale video data set is very computationally intensive. So in order to speed it up, we did a large-scale experiment in 2019 on the Summit supercomputer. At that time, that's the world's largest supercomputer. Okay? It has a pretty strong IBM Power 9 CPU. Each node has 6 V100 GPUs, okay? Pretty large memory, connected by InfiniBand. So there are several principles, okay, for training speed up, right? Like we mentioned in the training section, we want to have less flops, okay, so that we can save the computation time and also reduce the data movement. Okay, data movement, there are how many aspects? What are the aspects of data movement in this case? So we have two aspects. One is the I/O between the nodes. Okay? The other is the memory. Okay, and the other is the communication between the nodes. So I/O is between the disk and the memory. Okay, and the memory overhead is between the memory and the processor, and the communication is between different nodes. Okay, so for temporal shift module, we compared the throughput and the hardware utilization with baseline methods like I3D, okay, 3D convolution-based methods. So throughput is basically how many videos you can process, you can train per second, and utilization is the flops per second. Okay, and actually this TSM can outperform its I3D by a large margin for both throughput and hardware utilization. And TSM is also I/O light, right? So decreasing the total batch time. So here, the yellow part is the actual compute time, and the blue part is the I/O time, right? So we want to read less number of frames, okay, so that we can reduce the disk workload. This is showing the scalability as we are increasing the number of GPUs. Okay, the scalability is defined as the actual speed up divided by the theoretical speed up. For example, when we're having 32 GPUs, the theoretical speed up compared with one GPU is 32. Okay, and here we are having like 85% utilization, indicating that the actual speed up is 32 times 85%. Okay, TSM maintains a pretty good speed up utilization, more than 97%, right? And what is the reason for that? Compared with this I3D, right? It's a three-dimensional kernel, right? So the total tensor dimension is 5. But here, using TSM, we are reusing a 2D convolution neural net, which has a 4D tensor, right? And the temporal modeling is just achieved by shift. There's no actual parameter required for that. Right? Therefore, we can have a smaller amount of model size. And remember, during distributed training, we need to communicate the gradient, right? And the dimension of the gradient is the same as the dimension of the weight. We have 4-dimensional weight rather than 5. So we have a smaller 4-dimensional gradient as well, right? So smaller amount of gradient indicates that we have less networking bottleneck, right? Therefore, it's more scalable as we are increasing the number of nodes. So here is the large-scale training on the video results with only one node, which has 6 GPUs that require 49 hours and 15 minutes to train over such a big chunk of videos. Okay, and by the way, the data set is the kinetics, which has 240K training videos. We train it for 100 epoch. Okay, and this is the accuracy. The peak GPU performance is about 46 teraops per second. And we are increasing that to 256 nodes, which corresponds to 1,536 GPUs at the same time. Okay, and that requires only 14 minutes, just over a cup of coffee, right? We can achieve similar accuracy, okay? But the actual speed up is 211 times. Okay, so that shows the power of good scalability by designing the model that is communication efficient, I/O efficient, and also less flops, so that we can make it very scalable, utilizing a lot of GPUs to reduce the training time. Okay, so we also experimented. Can we enlarge the batch size? So when does it fail? Okay, we can enlarge the batch size all the way to 12K before the error goes up. And here we can also compare the I3D using the 3x3x3 kernel versus using 3x1x1 kernel. Okay? TSM is showing the number of GPUs versus the throughput, okay, videos per second. This is in log scale. So actually, the TSM is about 60% to 2.9 times faster than these baseline I3D methods. Okay, so from inference to training, now let's switch gear to try to dissect and understand how to explain TSM, right? So what is it looking at, and is it effectively capturing both the spatial and temporal information? Okay, so we find for this class, like predicting if something is moving something away, these are 1, 2, 3, 4, 5, like 8 frames. And here we are actually, we can dissect what TSM is looking at by looking at the final feature map before global average pooling. It's very accurately highlighting the region, spatial region, and also the temporal region that we are moving something away, like moving the cup away, moving some water bottle away, moving this basket away. Okay? Very accurate highlighting both in the spatial and temporal dimension. This is channel 446, pushing something to the left. So pushing the water to the left, pushing the mug to the left, pushing the box to the left. Okay? Very accurate spatial temporal modeling. So here we have a real life demo done by one of our lab mates. So he made a live demo for hand gesture recognition. Okay, you have to understand the video, otherwise you don't know whether it's moving left to right or swiping right to left. Okay? And he's using that for Google Map navigation. Okay? You can thumb up, you can zoom in, zoom out in the street view. You can drum the fingers to return to the map view. You can zoom in, you can zoom out, drum the fingers and go to the street view by thumbing up. Okay? It's running real time on HSN Nano. Okay? Imagine if you're in a car, you don't have to physically touch the buttons, but also you can just interact with the car by using your gestures. Something like this could be a very good final project. So we have also open sourced the code for this project. So if you want to do some gesture related final project, we can feel free to talk to us. Here is another real life demo on the something something dataset, which is giving a lot of labels such as moving, hitting something with something. We can predict very accurately what's happening in the video. Moving something away from something, covering something with something. Or rolling something. Hey, so if you're interested in some projects like that, feel free to talk to us. After introduce 2D CNN, 3D CNN, and the temporal shift module, let's look at other efficient methods for efficient video understanding. Just like SVD for 2D scenes, we can also do a kernel decomposition. Right? To decompose a 3D CNN kernel into 2 parts, okay? One is the 2D for spatial modeling. The other is the 1D for temporal modeling, right? So that we can have a lighter weighted module. Previously, say we have 3x3x3. Now we can just have a 3x3 temporal spatial modeling and a 3x1x1 temporal modeling, right? So if you can calculate the number of weights, previously you have 3x3x3, that's 27 weights. Now you have 9 plus 3 weights, right? It's much smaller amount of model size. It's lighter weighted, and actually it's easier to train than the 3D convolution. For example, the blue part is the error versus the number of training epochs. As we increase the number of epochs, the error is going to decrease. But this 2 plus 1D is actually having a lower, a faster decrease. It's decreasing the error faster compared with the 3D kernel, both for the um, train and also for the validation. So apart from decomposing from 3D to 2D plus 1D, there's also multi-scale modeling, right? The motivation is that we want to capture a large spatial resolution and also a large temporal resolution to watch as much as possible in the past and also watch the entire frame as possible, right? So that's very computationally heavy. So can we have a two-branch architecture, one branch focusing on each part? Okay, we can have a small spatial resolution. Just look at the ball part, the big picture. Okay, but very large temporal resolution. Okay, so small spatial resolution but large temporal resolution. The other branch can have a large spatial resolution. Okay, looking at the very fine-grained details of each pixel, but relatively less on the temporal dimension. Okay, this is combining these two branches. Okay, the first one is having a small temporal resolution. Okay, just a couple of frames in the past, but pretty large spatial resolution on the C dimension. Okay, but a very small T dimension. The other branch has pretty large T dimension, but a pretty small C dimension. Okay, we can combine these two frames so that combining them together, we can have as if we have a large resolution and also have a large temporal dimension. So this method share a very similar taste with this kind of decomposition, right? Modeling the temporal and spatial information using different computation. But we think it's fundamentally different to model the temporal information versus spatial information, right? But they also share a lot of similarities. They both have redundancy. Like spatially, the pixels does not change very suddenly, only at certain places. Like this pixel and this pixel, black and white, they change suddenly, but from here to here, it doesn't change suddenly. But temporally, like I cannot move at super fast speed, right? So adjacent frames, they also share a lot of similar information. So therefore, there's opportunity to decouple the modeling of temporal information versus spatial information. And the shift is another way that we find is super helpful compared with convolution to model those temporal information. Since these two modalities are fundamentally different, it's not necessarily to always use convolution, either 1D or LSTM or whatever, to model those information. Okay, so apart from the new design spaces, we also have neural architecture search, like we mentioned in the first couple of lectures in this course, right? So here we can search different dimensions and gradually expanding the following dimensions: temporal duration, the frame rate, the spatial resolution, the width, the bottleneck width, and the depth of the neural network to gradually improve the performance. And there are other efficient methods that try to skip these redundant frames, right? So rather than looking at each individual frame, lots of the frames are very similar, right? Like this swimming video. Okay, so we can just skip all those unimportant frames. Okay, we can actually use a smaller resolution or smaller capacity neural network to predict first whether it is important. Okay, and then only run this full classifier on those important frames to skip a lot of frames, non-salient segments. And there's another line of work using this spatial temporal redundancy across different frames, since assuming two frames are very similar, where at xt plus 1, it's basically xt plus a certain delta. Since delta is pretty small, and if everything is linear, we can assume we can compute only on this delta. Okay, so we can reuse the previous prediction plus this f delta, right? So since the change is probably only a few pixels from the previous frame to the next frame, we can have a much smaller theoretical flops to only compute on those pixels that get changed, right? So, but smartly doing that is very important because this delta might be very sparse. Okay, we might have to use sparse convolution to realize those theoretical speed up into measured speed up. All right, so that completes our first section, which is efficient video understanding. Basically, how to deal with temporal information, okay? And how to utilize those temporal redundancy using shift rather than convolution to understand the videos and model the temporal information. Now let's switch gear to talk about the third application that is very computationally intensive, which is generative models. Okay, we can do photo editing, we can generate new images, but they are computationally intensive. And how do we accelerate? How do we find those domain-specific opportunities to accelerate such generative models? And this is the plan for those generative models. So today we're going to first talk about those background. So what is the GAN model? And we are going to talk about those GAN compression, okay, with neural architecture search and also distillation. In the next lecture, we're going to talk about those any cost GANs, okay, to have dynamic cost. When you are doing the raw sketch, we can have a very fast real-time rendering, versus when we are finalizing our drawing, we can offer a high quality but slower generator. Okay, so given any cost, we can have a very smooth trade-off between the latency and quality. And next, we'll talk about our latest NeurIPS publication, which is spatially sparse inference, okay, to save the computation by taking advantage of those spatial redundancy. Since during photo editing, we are not editing all the pixels. Can we only do the computation on those edited pixels to save the computation? And how do we efficiently support those sparse operations brought by this partial editing? Okay. Finally, apart from this computationally expensive, GAN models are also very data hungry, right? Require tons of images to train a single GAN model. So we'll talk about data efficient training. Just use maybe a couple of images. In our example, use only 100 images. You can train a photorealistic image. And that could be another good candidate for final project. Okay, so background for this generative adversarial networks. Okay, so it has two components. Okay, we have a generator. We also have a discriminator. Okay, we can have both a real image and those fake image that is generated from this generator by feeding it with random input. Okay, and use the generator to generate a sample. Try to make it very similar to the original real image. And the job for the discriminator is trying to tell whether the image is coming from the normal distribution, the real image, or is it coming from those generated fake samples. Okay? So this discriminator and generator are actually acting against each other, where the generator is trying to fool this discriminator by thinking, oh, this is something that is actually real. While the discriminator is trying to be very picky, can tell apart the real image versus the generated image. So as training goes on, they both get stronger. Okay, so generator can produce very photorealistic image that discriminator is difficult to distinguish. And the discriminator is actually trained to be very strong if the generator is getting some poor result, it can immediately find this is a fake image. Okay? So in the end, we can feed random input, but it can generate a very photorealistic image. So let's see an example. Using random initialization, after a while of training, we can actually generate the handwritten digits by training an MNIST dataset. We can watch it again. Okay, so this is an example of learning to generate digits from the MNIST dataset. So apart from that, let's introduce two concepts. One is conditional GAN, the other is unconditional GAN. Okay, so the example we have shown just now, this is unconditional GAN, right? So we don't know whether we are going to generate a 0 or generate a 1. It's completely random. So we are feeding it with random noise, and then we can generate all kinds of different outputs. On the other side, conditional GAN is conditioned on certain inputs. For example, it could be the class label, so telling the generator only generate me some cats, or some segmentation map, or some strokes. Like this one, we are feeding it with some strokes. Okay, and this is telling we are conditioned on this input generate me some outputs, right? So here we are not only feeding with the noise, but also some label. Okay, the label could be the stroke, segmentation map, or the class label. Question? Yeah, you do need those. So let's see another famous conditional GAN called Gauss GAN for drawing. Right. So here we are having certain strokes. Then immediately we can get some grass, and then we can have a lake, starting with the sky, and then we can draw a line, fill it with green color, and then we can draw some mountains in the far, add some grass, draw a river. And recently, diffusion models, apart from the scan models, are becoming another popular branch for image synthesis and photo editing, right? So here, let's see. We're actually inserting a new dog in the image, but you can hardly tell this is something generated by the computer. So those generative models are much more expensive than recognition models, right? Similar for human. If you want to tell whether you are speaking certain language, that's very easy to do, right? But if you try to learn something to speak certain language by yourself, to draw something by yourself, is much difficult. Similarly, here we compare MobileNet, ResNet versus the computation, the parameters for like cycle GAN, Gauss GAN, and also the computation compared with these methods is about 2 orders of magnitude more than those recognition models, right? So accelerating and compressing such GAN model becomes very challenging and very crucial. So let's introduce the GAN compression method, okay? So which is trying to compress these conditional GANs. Let's review a little bit what kind of techniques have we learned so far, right? We learned pruning, we learned distillation, we learned neural architecture search, quantization, etc. Right? So here we are trying to combine these efforts together to have a holistic solution, right? So first of all, here we can use this neural architecture search to train a super generator that can include different number of channels. Okay, so this is the original model. Okay, this is our shrink the model. Okay, using the idea similar to once-for-all network, which we learned in lab 3, we can sample different number of channels. Okay, And finally, we can do evolutionary search to find the optimal channel number that is a good balance between the latency and also the accuracy, right? So previously, how do we supervise that? We have a loss, right? So here we are using the distillation method to try to train this supernet, right? So this is the teacher model, the pre-trained teacher model, the full model. And this is the partial model, okay, a student model, which is smaller than the teacher model. However, their number of channels doesn't match, right? So this can have a full channel. This is a partial channel. Therefore, we have to use this projection matrix, try to project the dimension so that the dimension actually matches, right? So that creates the teacher and student loss, the distillation loss between the teacher and students' outputs, right? We also have this reconstruction loss, right? So from the teacher, from the student, we try to make sure they can have very similar output. Okay. Finally, we can have this conditional GAN loss, similar to what we have described so far. Make sure the discriminator can tell whether this is fake or real image, and the generator can try to fool this discriminator. And after training this supernet, we can do evolutionary search, okay, to generate a pool of different generators. We may have a more number of channels, less number of channels. So every time we are sampling a different generator, right? And here we are focusing on the generator, since only the generator will be used at the inference time. For the discriminator, we don't have to compress it because the discriminator is not required at the runtime, at the inference time. So here are some examples of compressing the GAN models from originally. This is the pixel to pixel work. This is the input. This is the ground truth. This is from edges to the shoes, right? The original model's prediction is very close to the ground truth. And here we compress it by more than an order of magnitude. So the model is about 11.8 times smaller. But this is still very photorealistic. Maybe this one even look closer to the baseline. The shoe color get changed, right? So from this sketch, it's still pretty reasonable to generate such a shoe, although the color is different from the baseline. Similar for these boots, right? So this is from horse, zebra to horse, and horse to zebra, right? So given an input, which is horse, which is conditional GAN, and here the baseline, this is the GAN compression. This is the original cycle GAN, okay? Trying to generate a zebra from the horse, okay? And this is the result achieved by this GAN compression. It's pretty fine detailed from the zebra is very well maintained. Okay, similar for this darker one. Okay. However, if we naively shrink the channels and reduce the model by about 14.9 times, the result is much worse. Like those bands are much less clear compared with these ones. And this one, you can hardly tell this is a zebra, right? So naively reducing the number of channels doesn't work as well. But here, GAN compression can reduce the computation by more than 20x while maintaining the photorealistic quality of the generated image. So using this technique, GAN compression, we can also compress this GAN, right? So GAN basically, this is on the cityscapes dataset. Previously, we have talked about segmentation, right? Given the input, we draw the segmentation map, which is the car, which is the tree, which is the building, etc. Right? So here we are doing an inverse problem. Given this input, we try to generate the original image, right? So this is the ground truth image. Okay? And also on the third row, this is the output generated from the original GAN, right? So we can see the car is pretty well generated. The street, the other car over there, matches the ground truth pretty well. Although the ground truth is pretty bright on the facade, this is dark, but it matches with the ground truth segmentation result. Similarly for this one, although it doesn't contain very fine grain details, but it still is pretty accurate, although the road is a bit broken. So this is the baseline GAN model. And GAN compression can reduce the computation by about 8.8 times. Okay, but here the person is still pretty accurately generated, even contains more details compared with the baseline full model before compression. Right? And there's probably less distortion even compared with the baseline model. Okay? And the building contain as much as details compared with the baseline, even closer to the ground truth. So this is a real-time demo running this GAN compression on a Jetson Xavier GPU, okay, from a horse to a zebra. Originally, it's pretty slow because it requires 56.8 gigaflops per second, okay, which is pretty slow. FID is about the frames per second is about 12 frames per second. But after compression, we can reduce the computation to only 3.5 gigaflops. So that's 16 times smaller. Well, we have a 3x higher frame rate, right? So if you want to do some experiments for your final projects, feel free to contact us. We can give you access to those machines and those code. Oh, by the way, the whole code for GAN compression is fully open sourced. So feel free to use this code base to generate fancy images that you like. Okay, so we have some time to continue to talk about any cost GAN, right? So imagine we want to sometimes have dynamic cost, right, during the inference. Okay, can we have a smaller amount of computation and lower quality but faster response speed? Okay, versus when we are finalizing the image, we want to have a high quality. Although it can be slower. Borrowing from the idea from ray tracing pipeline, okay, people will get faster previews. For example, this one, by reducing the number of sampled rays. Okay, and this is very high quality, but it has a larger amount of sampled rays. And can we do the same for these GAN models? So the way that image editing works is as follows. So given an input image, okay, we can project the image into a latent space. Okay, so each point in the latent space corresponds to a different phase. And this is a high dimensional space where each dimension might be controlling different features. Some of the feature space might be controlling smile versus non-smile. Some dimension might control the hair color. Some of them might be controlling whether he or she is wearing glass or not, right? And then we can perturb the latent space so that we can change different features, like removing, changing the hair color, okay, and changing the age, etc. So we can run the full model during editing, where we hope we can immediately get the result after we draw some strokes, right? Tune some bars, right? It can be pretty fast. Running the partial model, the quality could be lower than the final version, right? So finally, when we are determined, okay, this is the image I want, I can run the full cost model, which is slower, but get pretty much higher accuracy or quality, right? And these two must be consistent with each other. This is for preview. This is for finalization. So the learning any cost again, there are several perspectives. right? So we want to produce consistent output at different resolution and different number of channels, right? Since the speed of a neural network is highly dependent on the resolution and also the number of channels. So this is the StyleGAN tool, which used to only feed those highest resolution, right? So from 256 to 56. Other work tend to feed all the resolution as well. But our approach is to sampling based multi-resolution, right? Since we want to make sure the model can not only produce high resolution images, but also it can produce low resolution images if the computational resource is low, right? So at the training time, we randomly sample high resolution or low resolution at the same time. So as a result, okay, so here is comparing different methods across diverse resolutions, and our method consistently outperform these baselines across different resolutions. Oh, FID is a figure of merit for determining the quality of a generated image, right? So it's evaluating how close is your generated image compared with those real images. So the data set consists of a bunch of real images, and then you run some predefined network like VGG to collect the feature, to extract the feature of each image, okay? And you have two sets of image. One is the baseline, one is your generated image. And for each image in both sets, you're going to extract, say, the VGG19, VGG16 feature, and then you compare those features to measure how close you are from real-world images. And okay, so we now have the different resolution. So and then we can support different channel numbers. But the problem here is that the original method, like StyleGAN tool, when it's generating those low resolution image, okay, it cannot generate a low resolution, right? If the model is trained to generate 256 by 256 image, it cannot generate low resolution image. Ours, in the contrary, we can generate across 256 or even 32 by 32 resolution image. And the only trick that we played here is by sampling different resolutions at training time, so that the model is adapted and know that at runtime I'm going to it's highly possible I can either run a smaller input or a higher resolution. So with respect to the channel, right? So here we are using similar approach as the once for all model, so we can sample adaptive number of channels during training. We use full model or partial number of channels. But the problem here is that using fewer number of channels will cause those inconsistency. Like full channel, this is generative images. This is the using half of the channel. The eyeglass suddenly disappeared, and the generated image doesn't look similar. Right? So here we want to make sure we can add a loss function, add a distillation loss to make sure the full channel versus the partial channel, they can match. Okay, so here is the distillation loss. And after applying the distillation loss, the full model and the partial model actually can generate very similar image. We encountered another problem. So we get a pretty bad FID for those for some of the small some of the subnets. And we retrospected and find that we are using the same discriminator for different generators, right? Imagine you have a very small generator, very weak generator. You should also use a weak discriminator, right? So the discriminator should be aware of the architecture of the generator. If the generator is small, then the discriminator should be more lenient, right? If the generator is pretty strong, the discriminator also has to be strong. So therefore, we have encoding of the generator's architecture encoded in one hot encoding, indicating the number of dimensions, passes through a few FC layers, and modulate the channels of the discriminator. Okay, so it's generator conditioned discriminator. And after applying that, we can fully recover the FID of partial generator. So this is showing the effect of any cost again using less number of channels, reduce the resolution. We can still generate very photorealistic image using only a quarter of the channel and using much lower resolution. And similar for this one, the generated car across different channels, different resolution, all look very photorealistic. So this is another demonstration about using 100% of computation, half, one quarter, only 19%, the quality of the generated faces. Okay, they look all very photorealistic, although we are here drastically reducing the number of computation. And this is the final demo we previously shown. We can do this photo editing by tweaking from different dimensions. For example, here we can make him smile by changing this bar to the right. Originally, it's pretty slow. It's running on a laptop, taking about 3 seconds to edit the photo, which is not real time. And then we can reduce the resolution and see how does that work. About 1.3 seconds, about 2x faster. Okay? We can further reduce the number of channels, and suddenly it's only half a second. Okay? Much faster, and the quality is still pretty good. We can further do other edits very smoothly locally on the laptop without requiring a workstation. We can also decrease the mustache. And finally, we can run finalize button to run the full model to give you the high quality rendered image. Require 3 seconds. Okay. And here we have more demos. And now let's get a new idea, right? So talk about the spatially sparse inference to take advantage of the spatial redundancy when we are only editing a smaller chunk of the region, right? So given a previous the full image, right? And now we only edited a small part of the image, and we try to generate a new image given our edits. So for photo editing, usually we are not editing 100% the entire image, but rather it's like this case where only a subset of the pixels, right? So the original DDIM that require more than 200 gigamax per step and require 50 steps to run such diffusion model to generate a photorealistic image, which is very computationally expensive. However, these unedited regions, they are almost the same, right? The feature map is almost the same. So actually, it's very wasteful if we have to compute all the computations on the entire image, right? So the insight is that since we're only editing a small region, a small portion of the image, is it possible to only compute the feature maps corresponding to the edited region, and we just ignore the computation on the unedited region, right? So to support that, we propose a sparse incremental generative engine, SIGE, right? So that we can reduce the computation to only work on those spatially sparse region, only the edited region, right? And also we can achieve good speed up on diverse platforms, Apple CPU, Intel CPU, and NVIDIA GPUs. And the way to achieve that, let's walk through how do we achieve that actual speed up. So this is the original image, right? This is the input activation, and output. For some convolution, this is the output activation, right? So on the other side, if we have a edited region, we want to add some cloud to this image, for example, we can get the difference mask. Okay, only these regions, okay, the pixel in those regions are different. So we want to only work on these edited regions rather than having to compute on the entire image, right? And we made that possible by actually chopping that into several pieces, okay, to the blocking, and then we reduce the region to only the regions that has been edited, corresponding to this red region. And then we gather those regions here, here, and here from the original image, so that we only run computation on the batch of these edited regions rather than having to run the convolution on the entire image. Okay? So that we finally can scatter the feature map back to the original image for a certain layer. And after a couple of layers, these sampled regions can be seamlessly integrated as the receptive field grows. The boundary will seamlessly merge with the original image so that we can get a final generated image adding some cloud to the original image without having to run the convolution on the full feature map. Question?
Sorry, could you repeat what is going on in that scatter operation?
Oh, so the scatter operation is basically putting this new convolved result with the pre-computed original image's feature map and scatter these patches to the original image. So that, correct. It's like merging the new feature maps with the pre-computed feature map. And during the merging, we only compute these newly edited patches, so we don't have to do all the computation. Okay, so let's see some results. So original image, okay, if we added about 11% of the pixel or 1.2% of the pixel by adding a Gemini. So the original DDIM, the diffusion model, requires almost 250 gigamax. But by using our approach, we can reduce the flops, the max to 61 gig versus 33 gig, almost 4 to 7x reduction of the flops. And of course, the smaller you edit, the larger you save. But if you edit the entire image, you don't save anything. So let's see another example, whether this method can it be combined with other approach like GAN compression, right? So fundamentally, they are working on different dimensions, right? So what dimensions is GAN compression working on? Is the channel dimension, right? Reducing the number of channels. Well, this SIGE method is dealing with this spatial redundancy, okay? Spatially sparse inference, right? So we can combine them together to further boost the compression ratio, right? So like we are editing about 1.18% of the image by adding another car to the original image, right? So given such segmentation map, GAN generate a new image corresponding to the segmentation map, right? So to generate this image from the segmentation map, originally that requires 281 gigamax, which is a lot. Well, ours, since we only edited a small region, okay, we can apply the spatial sparsity to this method to this generation, so that we can reduce the computation to only 15 gig by only computing this edited region, right? So GAN compression itself can reduce the computation to 31 gig, right? By shrinking the channel by building a SuperNAND once-for-all approach. Well, if we combine these two methods, GAN compression on the channel dimension, and SI on the spatial dimension, okay, here we can push the computation to only 5.59 gigamax, okay, which is 50 times smaller compared with if you have to run the full model on the full resolution image, right? So this is leading to a very significant speed up on different platforms, including the 3090 GPU, as well as the Apple M1 CPU, right? So this gray bar is basically the original GAN model, okay? Blue part is GAN compression, which we discussed in last lecture. This is our method, the spatially sparse inference. Okay? And we can combine them together to get even shorter latency. Right? On a laptop like Apple M1, we can reduce the latency from like 14 seconds. Imagine you need 14 seconds to edit the image versus only 0.37 seconds, like 1/3 of a second to edit a single image. That is amazing. Okay, so that will enable those photo editing on our laptops, on our iPad, okay, in real time, right? A very short amount of latency, very responsive, rather than having to wait a long time for those photo editing tasks. Okay. All right, so far, what is the common among these three topics? We talk about different aspects from channel dimension, from dynamic channel spatial dimension to reduce the computation of these GAN models, right? So beyond computation, what other aspects is expensive for GAN models? You need a lot of data to train the model so that it can generate new images, right? So it is not only computationally expensive, but also data expensive, right? So how can we save the amount of data and make it more data efficient? So that is the differentiable augmentation, which is targeting improving the data efficiency for those GAN models. And let's see how that works. The big picture and motivation is that big data is really expensive. It takes months or even years, okay, to collect a lot of data along with prohibitive annotation costs. So this FFHQ dataset contains more than 70,000 selective post-processed human faces, while this ImageNet dataset contains millions of images with more than 1,000 categories, right? So GAN model require lots of training data in order to work. Given a limited amount of data, the generated image quality is actually quite poor, right? So using 100 Obama faces, the generative model can only produce this low quality, non-photorealistic Obama faces versus the cats. If it is trained with only 100 images, you can imagine it's not producing a good model that can generate good cats and good dogs. Okay, and how do we improve such data efficiency? Imagine if you like a child to draw a cat, you don't have to train him or her with like hundreds, tens of thousands of images, right? A human can draw something by watching only a few cats and then probably can draw himself. Good question.
Are these, so if I were to take a look at each of the 100 Obama pictures in this data set, would I find one that pretty much matches each one of these four? Like, is the GAN basically just copying it?
Lots of the times, yeah, for the GAN models, it is remembering the input training data set. So that's a known issue for these GAN models. But with 100 images, it can not even remember them. A lot of distortion since the original training data set is not like this, showing that it is not even remembering very well since it is given so little, so few number of images.
So there's probably a picture in there where Obama's looking to the side in that specific direction, wearing that suit.
That's possible, but definitely the eyes are not like that.
Right.
That is to say, we need a lot of training data, like high quality training data, right? The quality may be already pretty good, but the amount of data is not enough, right? So again, quality will heavily deteriorate given limited amount of training data, right? So here we show the FID, which we discussed last week, which is describing how realistic the the image is compared with the real image, right? By comparing the VGG features. Okay, so the lower the FID, the better the quality, right? So with 100% of the training data, right, you get a pretty good FID, but with 20%, it deteriorates, and with 10% of the training data, it deteriorates even more. Right? The higher the FID, the better. The lower, the worse. Right? The lower the FID, the better. So we want to actually maintain the accuracy even given a small enough amount of training data for efficient deep learning, right? So let's see why, given limited amount of training data, the accuracy is poor. So let's dissect and understand the accuracy given by the discriminator, right? So a discriminator's accuracy will determine how strong the discriminator is, and on the other side will also reflect the strength, the quality of the generator, since they are both growing along with each other, right? So if the discriminator's accuracy is poor, I'm sure that the generator cannot generate good models either, right? So this is showing the comparison of 100% training data, okay, in blue and 20% in yellow, and finally 10% of training data in red, right? So as we are decreasing the amount of training data from 100% to 20%, right, we can see that this training accuracy actually increased a lot. It's overfitting, right? Well, the validation accuracy is deteriorated. This is 20%, when this is 10%, it deteriorated even more. So there is a very strong overfitting problem for the discriminator, right? Since you have only a couple of images, it's not enough to train the discriminator to generalize, right? So the discriminator completely just remembered probably a few images, whether it's real or fake, since it doesn't have enough data, right? So it doesn't generalize, okay? So the key issue to solve this problem is to be able to augment the data so that we don't suffer from such overfitting problem for the discriminator when there's a limited amount of training data. Okay, so how do we solve this overfitting problem? So that's a very classic question, right? So anybody has some idea how to solve this overfitting issue on images?
Shift, add noise, rotate.
Rotate, mirror, adding noise, jittering the color, called augmentation, right? So those kind of techniques are very effective, by augmenting your image, flipping from left to right, rotating it a little bit, etc. Right? So that's exactly what is commonly used in those discriminative tasks like detection, segmentation, classification. Right? So data augmentation is very effective to cope with the overfitting problem, right? But GAN is relatively challenging, right? It's not as straightforward as a discriminative model, like a classification model. You just shift, you just rotate, you just color jitter the input image. For a GAN model to work, there are multiple places where you can apply such distortions. Right? You can apply it to the generator, you can apply it to the discriminator. For the discriminator, you can also apply it either to the fake input, or you can put it in the real input, or you can put in both. Right? So where exactly should we apply such augmentation to the image for a GAN model remains to be a big challenge, right? So we have the generator, we have the discriminator, right? Previously, we have the input noise for the generator and generate a fake image. This is a real image. Discriminator try to tell whether this is a real image or this is a fake image, right? So here we can apply this augmentation to either the real image. We can also apply it to the fake image, right? And we can either let the generator know to backpropagate through all the way to the generator, or we don't need to let the generator know we are applying some noise. Right? So there's a lot of choices, making the augmentation quite non-trivial. So let's visit this thing from some simple case. For example, we just use the augmentation for the real image only, like applying this transformation, augmentation on the real image only, right? So let's see it again. Previously, there is no augmentation. Now we added some augmentation for the real image. Try to tell the discriminator, okay, the real image, we applied some augmentation. Hopefully, it can stop the overfitting, right? So can this solve the problem? And what problem will it? What new is the new problem is going to incur? So we did an experiment. We did color jittering. We also did the translation. We also did the cutout for this real image and feed it to the discriminator and try to see what the generator can do, right? So we plotted, visualized the result from the generator, and sadly we find whatever jitter we apply to the discriminator, that exactly gets reflected to the image generated by the generator, right? It's very interesting. The generator hasn't seen this at all, but since the discriminator thinks, oh, this is a real image because it has cut out, right? This is a real image because it has translation, right? So it cheated the discriminator thinking to think that a normal image should be something like this because all the real image that is fed into the discriminator has this kind of translations, jitters, cutouts, right? Therefore, it is treated to think these are the real image, and therefore the generator also generated images that has such property, right? So apparently, this method doesn't work. So how can we change it to improve over such distortions? Where else should we add such augmentation? To the generator's output. So it is here, right? Generators exactly, so that the discriminator can have a balanced input, right? So we can also apply the distortion not only to the input from the real image, but also the fake image. And so we add a translation or augmentation for both the real image and also the generated image, right? So let's see what happens here. So for the discriminator, okay, we try to see the accuracy, whether how well it distinguishes the real versus fake image. So it's a binary classification problem. It has very high accuracy on the augmented real image and augmented generated fake image, right? But if given the generated image but is not augmented, right? If it's not augmented, it cannot tell whether it is real or fake in a high accuracy, right? So this is still unfortunate, right? So the generator sees everything that has been augmented. If it is not augmented, if it's truly generated by the original generator, it cannot do it very well, right? So therefore, we should do something else, right? So far, the discriminator and the generator are not talking to each other at all, right? The generator is not aware there's actually some augmentation for its output, right? So the solution to that is actually we also, when we are updating the generator, we also want to backpropagate the gradient through this augmentation, right? So that the generator is aware that its output is being distorted, is being augmented by backpropagating the weight through this distortion and augmentation, right? Those augmentations are usually differentiable. For example, add some colors, you can do some rotation, you can do some shift or cut out, right? So those operations are actually all differentiable. So we can backpropagate the weight to the gradient to the generator, right? So now the generator is also aware of this distortion or augmentation, right? So we want to augment both the reals and the fakes, okay, for both the discriminator and the generator. Both of them should be aware of the existence of the augmentation, right? So 3 places we need to add this augmentation, right? So not only for real image, but also for fake image, not only the forward, but also the backward. We need to backpropagate through all sorts of jitters, color jittering, rotation, cutout, distortion, etc., all the way to the generator. Okay, so this is the difference from third approach versus the second approach. Okay, so by combining these three methods, we can have photorealistic generation using only smaller amount of data. Right? So we augment both the real and the fake image. We also should involve both the discriminator and also the generator to be fully aware of the existence of this distortion. And therefore, the accuracy, the FID of the GAN model, even with 10% of data, is not increasing as before, right? But it's staying relatively flat, meaning that the quality of the image is well maintained, even we are having a very small 10% of the training data. Okay. Okay, so here are more results comparing without data augmentation, without diff augment, the StyleGAN tool from NVIDIA, very popular baseline, using 100 Obama faces, 160 cats, 389 dogs. This is the original generative quality. But by applying diff augment with the same amount of training data, now we can generate photorealistic Obama, photorealistic cats, and photorealistic dogs. And actually, we are not just remembering the input images, but interpolates really well to those unseen, previously unseen faces, the directions of the faces, even from different seasons, from spring to the fall, even to the winter season, and here from different angles of the same building, from days to the nights, can very smoothly interpret. Okay.
How are these figures being made? Is it like traversing the latent space, or is it with
right? You can traverse the latent space to do the interpolation.
How do you pick where to go in the latent space? Or you just like
you start with some random signal, random number, right? And you continuously change a certain dimension, right? And then you can interpolate very smoothly to generate new images. Okay, all right. So that concludes our third part, the generative models. Okay. So in summary, 3D spatial redundancy for point clouds, temporal redundancy for videos, and also 2D spatial redundancy for GANs. And also the data efficiency is another perspective we can optimize.